Last time we gave the definition of a vector space. Let's review it real quickly. We said that if we have a set V that has two operations defined, one being vector addition and the second one being scalar multiplication, and this set satisfies 10 properties. The first two properties involve vector addition and scalar multiplication. That for any vectors x and y, the sum belongs to the space V. That for any vector x in your space V, alpha times x is a vector and it also belongs to V. We call this closed under vector addition and scalar multiplication. And then we have 8 more properties. The first one is that the vector addition is commutative. The second one is that the vector addition is associative. We have a 0 vector in that space, that set. For every element in our vector space, we have an inverse element. We see that scalar multiplication has to be distributive. This is a similar property, but it involves the sum of scalars. This is distributive. We see that we have scalar multiplication is associative. And the last property is that whenever we take a vector and multiply it by the number 1, we get the vector again. If you have all of these properties, then we call V a vector space. And the elements of V are vectors. We've already seen an example of this, a well-known example that you're familiar with, which is Rn. And when you think of vectors, you probably think of rays. This is a vector space. Now we're going to look at some vector spaces that are not so common that you probably haven't thought of as their elements being vectors. So the first vector space we're going to talk about is P sub n, or I'm just going to call it Pn. Let's let Pn be the set of all polynomials of degree less than n. So P is a polynomial. Let's review what a polynomial is. A polynomial, when it's evaluated at a number x, it looks something like this. This would be a polynomial of degree n minus 1, assuming that this coefficient here is not 0. So this would be a polynomial of degree less than n. So what would the space P sub 3 look like? So P sub 3 is a set of all polynomials such that P of x is equal to a0 plus a1x plus a2x squared, where this a0, a1, a2 belongs to the real numbers. We're going to show that P sub 3, with the field of scalars being the real numbers. Remember, if I don't write what the field of scalars are, then you assume it's the real numbers. So we can even put this down. Field of scalars. It's the real numbers. This is a vector space with the following vector addition and scalar multiplication. So our elements in our vector space, P sub 3, or our set, they look like this, P and Q, but we evaluate it at a point. So vector addition, how we add P and Q, well, when we evaluate it on x, we're going to evaluate P on x and add it to Q of x. For scalar multiplication, when we take a scalar and multiply it by a vector in P sub 3, if we evaluate it on x, it's the same thing as evaluating p on x and then multiplying it by the scalar. So this is a vector space. We're not going to prove that it's a vector space, but let's talk about a couple of things. Like, obviously, p plus q of x, this is commutative. So one of the first rules, I think, was to show that p plus q is equal to q plus p. So you can see that p plus q of x is p of x plus q of x, but you can rewrite this to q of x plus p of x, and this is q plus p of x. So since this holds true for any value of x, then p plus q is q plus p. You would show the rest of the properties in a similar way. So let's look back at the properties really quickly. You should keep these properties either written down or beside you like the textbook. So we showed this one. You can show this one in a similar way. You would do p plus q plus z evaluated at x, and show this side by just sending in that x to everything using what you know about polynomials. There is a unique 0. So the 0 function evaluated at x, we're just going to let it be 0. So then p plus 0 of x is p of x plus 0 of x, which is just p of x plus 0. Which is p of x. And so this is true for any x you choose. So this one's true. And you would continue in a similar way for the rest of them. Obviously, when you add two polynomials, so the very first two conditions you have to show, which is that the sum of two polynomials belongs to the vector space, that's true, right? Because if you have a polynomial of degree less than 3, and you add it to another polynomial of degree less than 3, it's also going to have a degree less than 3. Okay, you're never going to get anything higher than that. And multiplying a polynomial of degree less than 3 by a number won't change the degree of the polynomial. So it does satisfy these two conditions. So let's scroll back down. Let's look at another example. We can talk about matrices. Matrices, n by n matrices, they are a vector space. They're a vector space when you let the vector addition be the following. For matrices A and B and Rm by n, A plus B is exactly how we defined A plus B when we first started talking about matrices. So just the normal matrix addition. Scalar multiplication, again, if I don't specify where the scalar is coming from, we assume the scalar is a real number. So we take a scalar and multiply it by a matrix. This is normal scalar multiplication. So like 3 times the matrix A, you would send that 3 to all of the rows. That's what we're talking about when we say scalar multiplication. We are not talking about vector multiplication. So a vector space does not have a multiplication defined when it comes to vectors. We only multiply when it comes to scalars. You see this? This is a scalar. Of course, we know that we can multiply matrices. A times B. But vector spaces don't have, you could always add more properties to a vector space, but we're not talking about vector multiplication. When you add a multiplication, you call the space an algebra. So a vector space with a multiplication is an algebra, but we're not worried about vector multiplication. We're only worried about vector addition and scalar multiplication. Now this is a vector space. Why is it a vector space? Most of these properties we already know. We know that A plus B, when we add two matrices, is B plus A. We also know that it's associative. We know that if we take an m by n matrix and add it to another m by n matrix, we get an m by n matrix, so it's closed under vector addition. When we multiply by a scalar, we don't change the size of the matrix. It's an m by n matrix, so it belongs to that set. We could check all of these properties. We could multiply by a 1 and we get this vector again. Multiplying by a scalar, if we do something like 3 times 5 times A, it's the same thing as 3 times 5 times A. Of course, you would want to do this in more general for any scalars, but you know this is true, and that's one of the properties. So you could check all of the properties. I think the only strange thing you might think of, because you say, oh, well, it seems obvious that matrices satisfy all these properties, is thinking of matrices as vectors. So calling these elements vectors. Another example of a vector space is the set of continuous real-valued functions defined on this interval. So for example, if we have the interval from A to B, an element in this set would be this one, f of x is equal to x. You could have any kind of continuous real-valued, let's call this q of x, function, but it only has to be continuous and continuous on this interval. So of course you could have something like, let me do it in a different color, as long as it's continuous on your interval. Call this r of x. Okay, again, the vectors in this space are going to look like letters, like f, and then we evaluate it on x. So let's talk about the vector addition and scalar multiplication. This is going to be very similar to polynomials. So our vector addition is going to be f plus g of x is f of x plus g of x. And scalar multiplication, alpha times f of x is alpha times the function here, f of x. So the difference between this and polynomials, obviously, you don't have to have integer coefficients. Integer powers. So something like, as long as a is not equal to 0, an example, 1 over x, obviously that's not a polynomial. That would work if a is not equal to 0. You could do f of x is e to the x. That would work for any interval, and so on. So this is not a polynomial. Again, you would prove this in a similar way as the polynomials. That is a vector space. We're going to look at some non-examples, and we're going to show that these are non-examples. This is probably more along the lines of what I would ask you to do. I might ask you on your homework to show that one set is a vector space, because there's a lot of stuff to do, but it's easier to show that something's not a vector space, because all you have to do is find one property that it doesn't obey. And that's what we're going to do with these sets. So this, I think, is number 10 in your book, in this section. And it says we're going to let V be all the vectors in R2. So we're familiar with R2. But we're going to change the vector addition. So we know that V is a vector space with the regular addition, where we have x1 plus y1 is x1 plus y1, and x2 plus y2 is x2 plus y2. So we're using the same set, but we're changing how we add vectors. And we're going to let scalar multiplication be the normal scalar multiplication. We send in alpha into everything. And I want to show that this is not a vector space. How can I do it? Well, I need to find a property that it doesn't obey. So you want to look back at all your properties, make sure you have the properties in front of you, and let's talk about them. So first off, first thing I would check is if this vector space, if the set is closed under vector addition and scalar multiplication, okay? So you want to say, well, first off, if we add two vectors in R2, does this belong to R2? Does this sum? And the answer is yes. If we put anything here and a 0 here, well, 0 is a real number, so it is in this set. And scalar multiplication is in this set as well. So this belongs to R2, so it is closed under addition and scalar multiplication. Now, since we know that R2 with the regular vector addition and the regular scalar multiplication is a vector space, you don't really have to worry about figuring out some properties involving scalar multiplication. It's this addition that's strange, and that's what's going to change. You have to find something involving the addition to find something that doesn't work. So let's see. Obviously, if we put these in reverse order, we're going to get y1 plus x1 0, which you could say is y1 y2 plus x1 x2, but it could also be a lot of other things as well. It could be x1 5 and y1 10. I think the easiest thing to show here, at least in my opinion, is that it doesn't satisfy that we have a 0 vector. Let's see that. So remember that for something to be a vector space, I think this is property 3, there has to exist a vector 0 such that x1, x2 plus 0, 0 is equal to x1, x2, right? Because this is x and this is the 0 vector. And we get the vector x. But there's actually no vector. Here I'm assuming it's 0, 0, but there's actually no vector that will give us this vector back, because we always take whatever was here and force it to equal 0. So let's see that. So following this vector addition, x1, x2 plus 0, 0 is equal to x1, 0. If x2 is not equal to 0, x plus 0 does not equal to x. Can we change this? Is there another vector that works as a 0 vector? And the answer is no. No matter what you choose, this one has to be 0 in order for you to get this x1 here. But whatever you choose here, let's say you put 27, you're still going to get 0 here, because that's how this vector addition works. So there's no 0 vector. So there's no 0 vector, which tells you that this is not a vector space. R2 is not a vector space with this vector addition and scalar multiplication. We know it is a vector space with the normal vector addition and scalar multiplication. But when we change the way we add vectors, at least in this particular way, it's not a vector space.